Hey, class. Well, happy Friday, everyone. So, today is day 16, but who's keeping track, right? Today we're going to do section 4.4. So the homework for today's material will be due in 6 days. I just posted an announcement that homework 3 is graded, so as usual, I'll give you 3 days to request regrades on it if you believe some of it has been graded in error. You had 2 assignments that were due yesterday, but you can still get them in today for a small penalty. And your next homework, unless I'm mistaken, is due on Sunday. And then written homework is due on Thursday, as usual. So, any stuff or things before I get started? I mean, other than that. All right. So let's talk tangent planes and linear approximation. Everything that we're going to do today, here, now, has an analog from 10a. So I'm going to repeatedly remind you of what the analogous thing that you learned back in 10a was, and then I'm going to show you the higher dimensional version. Hey, I thought I reformatted this. Wait, is this the right freaking page? Ah, use this one. Okay. Okay, so let me remind you of what you did back in 10a as it pertains to tangent lines and linear approximation. So in 10a, you looked at a function of one variable, let's say f of x. And if you pick some point on the x-axis, say x naught, you could form the tangent line to the graph at that point. Let's call that line L of x. Then you learned in 10a that L of x had the following formula. So the slope of the tangent line is equal to the slope of the graph at that point, f prime at x naught. And if you imagine taking a magnifying glass and zooming in really close on the graph, you would see that the tangent line and the original curvy function coincide very closely near the point of tangency. Near the point of tangency, the two lines would look almost identical. In Desmos, for example, no, this is not the one I want. Here, this one. This is a graph of sine, and I formed the tangent line to the graph of sine at the point pi over 4. All I wanted to show you is what happens if you zoom in, just how close these two coincide once you get close enough. Okay, so that's the point. There, you can barely tell the difference between the two curves once you zoom in close enough, is the point that I wanted to impress here. So that's all one-dimensional review. Now let's step it up to 2D. First thing, the tangents are not going to be lines anymore. So what's sort of the next dimension up in terms of linear shapes? Well, it's like the two-dimensional analog of a line is a plane. We're going to have tangent planes now instead of lines. Okay, so here's a picture of what a tangent plane to a graph at a point might look like. In fact, let me give you a little 3D tour. Here, let's use this one. So here's some graph of some random function. It doesn't even matter, but, or it doesn't even matter what function is. I just wanted to show you what the tangent plane to the graph looks like at various points. And it's supposed to just barely touch the graph at the point of tangency. The book has a derivation of what its formula should be. I'm not going to show you that. I'm simply going to give you the formula in the interests of time. So here's the formula for the tangent plane. Let's say we want the tangent plane to the graph of f of x and y at some point on the graph, say where x is equal to x naught and y is equal to y naught. Which means that the z coordinate is f of x naught, y naught. I don't need to name this point. Then here's the formula for the tangent plane. Z is equal to f at x naught, y naught, that's just some number, plus the partial derivative of f with respect to x at x naught, y naught, times x minus x naught, plus the partial derivative of f with respect to y at x naught, y naught, times y minus y naught. Now, again, like I said, I'm not going to prove it to you, but you can see proof details in the book on page 391 if you're interested. It also looks a little bit like the previous formula, if I can show you that for a second. Imagine that this term is like the x derivative, and you added another term that's like the y derivative, and multiplied it by y minus y naught. So let's practice using this formula and come up with the equation of a tangent plane. How about to f of x equals x squared plus y squared? First, what's the graph of f of xy look like? Yeah, me say? Contours are circles. So the graph, since this is a function of two variables, it's going to be the graph is going to be a surface that lives in 3D. Spheres, another special one. I've shown you this one, and I've shown you spheres before as well. Spheres have like square roots in them. Oh, it's a paraboloid. That's correct, yes. So this is supposed to be, it's kind of like the 3D version of a parabola. Okay, so let's just plug this formula into the formula that I gave you and crank out the answer. So I'm going to need this, and this, I guess. Yeah, those will be the three things I need, where 1, 2 is like my x naught, y naught. Here, in fact, let me just call this x naught, y naught equals the point 1, 2. So f of 1, 2 is 1 squared plus 2 squared, which is 5. I'm going to need the x derivative at that point. So first, I'll just calculate what the partial x derivative is, and it's 2x. So at the point in question, we get 2. Similarly, I'll need the y derivative. Partial f partial y is 2y. So at the point in question, it's equal to 4. So my tangent plane is z equals, let's see, 5 plus 2 times x minus 1 plus 4 times y minus 2. And you know what, let's verify this graphically while we're at it. So here's a paraboloid. Here's our paraboloid, x squared plus y squared. And let's see, we're interested in the point where x, y is 1, 2. Like right there. And let's have it show the tangent plane. So that's the tangent plane. That's actually the software calculated tangent plane, but I can plug in the one that I calculated, and we can check that they are the same. So let me just do that. Oh, in fact, it looks like I already did right here. So remember, it was 5 plus 2 times x minus 1 plus 4 times y minus 2. So that does indeed look like it coincides with the one that the software calculated. Oh, wait. All right, let me ask you a question about this tangent plane. What's its normal vector? In fact, let me remind you something about normal vectors to planes. Recall that the normal vector to the plane ax plus by plus cz plus d equals 0 has normal vector ABC. So what was our normal vector? Sorry, what was your name? Oh, yeah, Gavin. Oh, yeah. What were you going to say, Gavin? Let's see. It'll be the, okay, the 2 is the coefficient of the x. 4 is the coefficient of the y. What's the coefficient of the z? I guess it might help if I move all the terms to one side in this equation to write it as 2x minus 1 plus 4y minus 2 minus c plus 5 equals 0. So that might make it a bit more apparent what the coefficients are. So what did we say it was? Okay, 2, okay, good. We have a 2 on the x, a 4 on the y, and a negative 1 on the z. So our tangent vector is 2, 4, negative 1. And notice that the 2 there was the partial derivative of f at x. And notice that the 4 there was the partial derivative of f at y. And that's no accident. So I'm now going to give you a formula for the normal vector in general for any graph. So for any function f, the tangent plane will have the following normal vector. It's given by n equals, the first component is the x derivative, evaluated at the point in question. The second component is the y derivative. The third component is just -1. So again, I'm not going to prove this, but I offer up the example that I just did as sort of a demonstration of why it's at least believable. So do you all find this formula believable, given that that's what happened here? Okay, cool. Then that will have to do for the moment. Also, a bit of terminology. This normal vector is normal to the tangent plane. We'll also describe it as being normal to the surface. So previously, we learned about normal vectors to planes. Now, today, we just learned what it means to be normal to an arbitrary curved surface. The image of what a normal vector looks like is it kind of like makes a right angle with the curved surface, if you can visualize that. So this is like what a normal on the side of a sphere would look like. It's perpendicular to the surface of the sphere. That's the same as saying it's perpendicular to the tangent plane to the sphere at that point. Now, remember, normal vectors are not unique. Every time I say the normal vector, I really should say a normal vector, because you can always multiply a normal vector by a scalar and get another normal vector. So in particular, I could take the negative of this normal vector, and that would be another normal vector. So negative fx, negative fy, positive 1. That's also a normal vector. It's also normal to the surface. It's helpful if you have some physical intuition for what the normal vector and the tangent plane at a point are or look like. It's not absolutely necessary, but it's certainly helpful in this class. So I have a question. What's the tangent plane and normal direction to the paraboloid, the same paraboloid, x squared plus y squared, but at the origin now? So what's the normal at the origin? Origin is down there. Oh, that is the normal direction, yeah. And the tangent plane? Is the xy plane, z equals 0. Cool. Okay, so yeah, if I plug in 0, 0, there's the plane z equals 0. And indeed, the normal direction is in the k direction, k hat direction. Warning, tangent planes don't always exist. Same problem arose in one dimension. For example, suppose you wanted the tangent to the graph of absolute value of x at the point 0. The graph of absolute value x looks like a V. So it doesn't have a well-defined tangent line at the origin. We would say it's not differentiable at that point. So the same problem can arise in 2 dimensions, or in functions of 2 variables, rather. For example, how about with the cone square root x squared plus y squared? This is another one of those shapes which is a common example in this class. There's certain shapes that come up a lot. You know, paraboloids, spheres, cones is another one. And I believe you've seen this on the homework. So let me show you the graph of square root x squared plus y squared. It's kind of like the 3D version of the absolute value graph, actually. There's the cone. And if you zoom in at the origin, it's got a sharp point right at the origin. So there's not going to be a well-defined tangent plane right at the origin. Let me make a quick note of the case of implicitly defined surfaces. Because not all surfaces are graphs. You know what a graph is? A graph is the set of points where like z is f of x and y. Not all surfaces are necessarily expressible in this form. So more generally, you have implicit surfaces. Implicit surfaces are just equations that relate x, y, and z. Or sorry, one equation that relates x, y, and z. So it's something of the form some function involving x, y, and z equals 0. So for example, x squared plus y squared plus z squared equals 1. AKA the unit sphere would be an example of an implicitly defined surface. So graphs are actually special cases of implicitly defined surfaces. That is, surfaces where you can express z as a function of x and y, those are also implicitly defined surfaces. You can see that if you just take the z in this equation and move it to the other side. So then you'll have f of x and y minus z equals 0. In other words, some expression involving x, y, and z equals 0. So you would just set the left-hand side equal to f of, capital F rather, of x, y, and z. The thing is, there's actually a nicer formula for the normal to a surface if you're dealing with an implicit surface. And that formula is the following. The normal to an implicit surface, as described above, is the vector whose components are the three respective partial derivatives of the function. So this is actually a nicer formula for the normal than the earlier one I gave you. That's why I wanted to mention this thing about implicit surfaces. I think I took most of the problems off the homework that involved implicit surfaces in the interests of time, or at the least any problems that remain on the homework that have to do with implicit surfaces can also be solved using other methods, but I still felt that it was worth mentioning this because it provides a more elegant way to solve some of your problems. It's a little bit faster in some cases. Let me show you an example. Say I want to find a normal to the unit sphere. How about at the point 1, 0, 0? So here's the equation of the unit sphere. So I can calculate the normal vector. It's pretty easy. Okay, so if x squared plus y squared plus z squared equals 1, then x squared plus y squared plus z squared minus 1 equals 0. So this is like my f, capital F. So that's what I would plug into this normal formula. So setting capital F to be x squared plus y squared plus c squared minus 1, we get that the normal vector is 2x, 2y, 2z. So at the point 1, 0, 0, it's equal to 2, 0, 0. And there, you got your normal vector. The picture, by the way, looks something like this. Let's say there's the unit sphere. The normal vector at the point in question would be like that. Okay, so any questions? Then let's start talking about approximations and then later differentials. Because remember how I started off this lecture by showing that if you zoomed in on the linear approximation near a graph, that the line and the curve were nearly identical. Same thing with planes. So really near the point that you're forming the tangent plane, the two are very close together. So you can use one to approximate the other. What I'm telling you is the fact that you can use tangent planes to approximate the function near the point of tangency. This is the same reason that we have flat earthers. Yeah, I mean, because the Earth looks flat from our perspective. It looks like we live on a plane. But really, we're just confusing a sphere for its linear approximation. So that's what happened with flat earthers. I'm sure they were oversold on the linear approximation. Let's continue to use the paraboloid example and approximate 1.01 squared plus 1.98 squared. So I'm going to use the tangent plane formula that I found before. What was it? It was z equals 5 plus 2x minus 1 plus 4y minus 2. So I'm just going to plug in 1.01 for x and 1.98 for y to obtain my approximation. That'll be 5 plus 2 times 1.01 minus 1, 4 times 1.98 minus 2. That's 5 plus 2 times 0.01 plus 4 times negative 0.02. That's 5 minus 0.06, which is 4.94. In this case, it turns out it's also pretty easy to compute the value directly. So let's compare this with the true value. Which I'll just use a calculator to find. It's 4.9405. So pretty close to the approximate value. You know, they were only off by 5/10,000ths. So now I'm going to show you some notation and terminology related to the concept of differentials. And I think I'm going to pause for a minute and review some 10A material first. So let me review the concept of differentials in 10A for a moment. So suppose that y is a function f of x. Suppose that x changes by a small amount, delta x. Well, then y is going to change a little bit as well. So letting delta y be the change in y, that is, the difference between f at the new value and f at the old value, we can restate the linear approximation. The linear approximation, using this notation, states that the change in y is approximately the derivative of f at x times the change in x. This expression right here is simply a restatement of the fact that the linear approximation is approximately equal to the function. Equivalently, it's a restatement of the definition of the derivative. So hopefully there's nothing mysterious about this. You could also write this expression using so-called differentials. So maybe you've seen these before. They're a little bit weird. They're mainly just notation. So differentials are infinitesimally small quantities. Sometimes they're called infinitesimals. So they're not quite zero, but they're smaller than any other number, than any other positive number. If you replace the deltas with d's, then this expression becomes exact as a statement about differentials. So you might have seen this written before. It's mainly just notation. It tells you how y changes when x changes. So now let me try and explain the higher dimensional analog of this concept. Once again, I'm going to first write things down using deltas. Suppose that z is f of x and y. Suppose that x and y both change by small amounts, delta x and delta y respectively. Well, then z changes as well. If this is the xy plane, maybe initially x and y were right there, but you increase x by an amount, delta x, and you increase y by an amount, delta y, and you end up at some new point where the function has a new value. So the difference in the value of the function at the new point and the value of the function at the old point is the change in z, the corresponding change in z. A restatement of the linear approximation that I wrote earlier is that the change in z is approximately the partial derivative of f at the point in question times delta x plus the partial derivative of f with respect to y at the point in question times the change in y. So this expression, this is just exactly the statement that the tangent plane is a good approximation to the function near the point of tangency. I hope you can see that. All I did was, let me, if I can scroll up for just a minute. All I did was subtract f of x naught y naught from both sides of this equation, okay, to get that one. So we can again express this in terms of differentials if we now replace all the deltas with d's. And it then becomes exact now that these are infinitesimal quantities. And it reads dz is f sub x dx plus f sub y dy. Hey, now you're doing calculus, man. Like, doesn't this look so much more elegant than like that complicated tangent plane formula? This is a nice, compact way of expressing the core concept here. But I like it when things look elegant. So, yeah, let me show you an example of the use of this equation. How about with our good old friend, the paraboloid? So that was z equals x squared plus y squared. If z is x squared plus y squared, then dz, which is fx dx plus fy dy, so let's see, the x derivative is 2x. The y derivative is also, well, the y derivative is 2y. So I get 2x dx plus 2y dy, which I also wrote right here. Also, using this notation, using the delta notation, let me just point out what the deltas were in example 4 here. This would have been like the delta x term, and this would have been the delta y term. And, oh, could anyone spot what delta z was? The change? How much did z change? Remember, delta z was approximately, sorry, I said that question wrong. Can anyone tell me what we approximated delta z by? I should have said approximated. And the linear approximation says delta z is approximately fx delta x plus fy delta y, which was 2 times 0.01 plus 4 times negative 0.02. So what did we approximate the change in z by here? Initially, it was 5. Like f of x naught, y naught was 5. We moved over a little bit to a new point. How much did the function change by? Approximately. Sorry, I should say approximately how much did the function change by? Yeah? 0.06. Sorry? 0.06. Uh-huh. And did it go up or down? Sorry? I mean, you're right. It changed by 0.06. Did it increase or decrease? It did. Cool. Very good. Yes. So that's why you're right. So it came out to be negative 0.06 was the approximate change in the function. Here, that the exact value was pretty close to that, but the approximate value was negative 0.06. Let's see. Anyone recognize where this picture's from? It's log. You guys were all deprived as children if you didn't watch Ren and Stimpy growing up. Yeah. You guys don't even know. Probably raised on freaking Teletubbies and like, oh, what's the Roblox? I don't know.
It's Lego Ninjago.
What?
Lego Ninjago.
Okay, I'm just saying, we had some edgy stuff on TV when I was a kid, like Ren and Stimpy. That show was cool. So that show would totally be canceled today. So let me show you. Let's see if I got 6 minutes. Okay, yeah. So suppose you have a log, which is a cylinder, and its height is 4 meters, and its radius is 2. Well, except you're not super sure about that height and radius. Let's say that for whatever reason, like maybe you asked a kid to measure it, there's a certain degree of error in those measurements for the height and the radius. we're going to approximate how much error you expect to find in the volume of the cylinder. So the volume of a cylinder of height h and radius r is pi r squared h. V is pi r squared h. You can view this as a function of two variables, r and h. If r and h are both only accurate to within plus or minus 1 centimeter, then let's see how much deviation we can expect to see in the volume. So delta V will approximately be dV dr delta r plus dV dH delta h. This is equal to 2 pi r h delta r plus pi r squared delta h. So if we're assuming that the height is 4 plus or minus 1 centimeter and the radius is 2, also plus or minus 1 centimeter, then the approximate change in the volume is going to be 2 pi times 2 times 4 times 0.01 plus pi times 2 squared times 0.01, which comes out apparently to be about 0.63 meters cubed. They have some homework problems where you're asked to estimate, like, what's the worst error you could expect to see in some function of several variables like this. So you just do the linear approximation in the worst possible case. So suppose that both the measurements are as off as they could possibly be. The last thing that I want to mention is the 3D differential formula. So it looks a lot like the two-dimensional one, except now, if we're looking at a function of 3 variables, well, we're just going to add a third term. Here, let me scroll up for a second. Just add a third fz dz term. And we get that if w is f of x, y, and z, then dw is fx dx plus fy dy plus fz dz. You could probably guess what the differential would be if it was a function of 4 variables now. But the last thing I want to do, and I ask you to do something similar on the homework, is apply this formula. How about to the volume of a box? If the sides of the box are L, W, and H. So suppose you have a box of dimensions L, W, and H. Then the volume of the box is L times H times W. Viewing this as a function of these 3 variables, we can write down what the differential volume is. You know, it'll be like FL dL plus FW dW plus FH dH. So that comes out to be, let's see, WH dL plus LH dW plus LW dH. And there's your differential volume of this box. It tells you the rate at which the volume is changing infinitesimally for these small infinitesimal changes in the length, width, and height. And that is it. Let's stop it here, right on time. Have a nice weekend. Have a nice Halloween. I guess you're going to have to celebrate Halloween this weekend, huh?